What if the universe is not everything we thought it was? What if the stars above you are not simply scattered across an endless universe, but are part of something much larger, something so enormous that there is no way to stand outside it, something with a boundary we could never see? And what if that boundary is the event horizon of a black hole? It sounds impossible. A black hole is supposed to be a place where matter collapses, gravity becomes overwhelming, and even light cannot escape. So how could an entire universe possibly exist inside one? The strange answer is that some physicists have proposed exactly that. Not because they found a giant black hole surrounding the universe. They haven't. Instead, they found something much more unsettling. When physicists push Einstein's equations to the most extreme conditions imaginable, they discover that black holes and the birth of universes may be connected in ways we still do not understand. Some theories suggest that the Big Bang could have been the result of a collapse inside another universe. And if that were true, our universe might not have been born from nothing. It might have been born inside a black hole. But before we go any further, there is something important to understand. This is not an established fact. Scientists have not proven that we live inside a black hole. The evidence is nowhere near that strong. What makes the idea fascinating is that it emerges from real physics, real equations, and real questions about the beginning of space and time. And the deeper we go, the stranger the story becomes. Because to understand how a universe could exist inside a black hole, we first have to understand what a black hole actually is. Imagine taking a star many times more massive than our sun for millions of years. Its immense gravity pulls everything inward, while nuclear fusion pushes outward, creating a delicate balance. But eventually, the star runs out of fuel. The outward pressure weakens. Gravity wins. The star begins to collapse. And if the remaining core is massive enough, the collapse can continue until an extraordinary object forms. A black hole at its center. According to classical general relativity, matter is driven toward a region called a singularity. A black hole is not simply an object sitting inside space. It is a region where space-time itself has been shaped by extreme gravity. And that distinction becomes incredibly important when we start asking whether an entire universe could somehow exist inside one. Because our universe is also a place where space-time is doing something extraordinary. It is expanding. Galaxies are, on average, moving farther apart. Space itself is stretching. When astronomers look deep into the universe, they see a history that stretches back billions of years. The farther they look, the younger the universe appears. Eventually, that cosmic history leads us toward an extremely hot, dense early state, the Big Bang. But there is a problem. The Big Bang theory tells us how the early universe evolved. It does not necessarily answer the ultimate question of why there was a universe in the first place. And when we try to push our equations all the way back to the beginning, classical general relativity leads us toward a singularity, a point where density becomes infinite. Temperature becomes infinite, and our familiar understanding of physics breaks down. That is not necessarily telling us that the universe literally began as an infinitely small point. It may instead be telling us something much more important. Our theory is incomplete. We need a theory of quantum gravity, a theory that can describe gravity when space-time itself becomes subject to quantum effects. And scientists still do not have a complete one. This is where black hole cosmology enters the story. One possibility is that the apparent singularity inside a black hole may not actually be the end of physics. Perhaps something happens at extreme density that prevents matter from collapsing forever. Perhaps the collapse reaches a limit. And instead of continuing inward forever, the matter could undergo a bounce. Imagine squeezing a spring. You push harder and harder. The spring compresses. But eventually, something pushes back. Now imagine a similar idea at a scale beyond anything we can experience. Matter collapses. Density rises. Space-time becomes extreme. And instead of disappearing into an infinite point, the collapse reverses. A new region of expanding space-time could emerge. New universe. This is one of the ideas explored by physicists such as Nikodem Popowski, who has investigated models involving torsion and Einstein-Cartan gravity. In these models, the extreme conditions inside a collapsing object can produce effects that prevent an infinite singularity from forming. The result can be a bounce. And that bounce could look, from the inside, something like a Big Bang. Think about what that would mean. From the outside universe, there would be a black hole. From inside the black hole, there could be an expanding universe. The two descriptions would be completely different perspectives on the same physical process. And suddenly, the Big Bang would no longer have to be the absolute beginning of everything. It could be the beginning of our particular universe. A universe born from something that existed before it. But there is a major problem. If our universe were inside a black hole, where is the black hole? Why can't we see its event horizon? Why can't we simply look outward and find the enormous object containing us? The answer proposed by these models is deeply strange, because the event horizon would not necessarily appear as a giant wall surrounding us in space. If the entire space-time we inhabit is the interior region, then the geometry of that space-time is fundamentally different from simply being inside an ordinary room. We cannot step outside our universe and look back at it. We are part of the space-time being described. It's similar to asking a two-dimensional creature living on a curved surface to point toward the direction that leads outside its entire surface. The creature may be able to measure curvature. It may discover that something about its world is strange. But it cannot simply leave the surface and look at the whole thing from the outside. Our situation could be even stranger. We don't know whether there is an outside in the conventional sense at all. And this leads to one of the most fascinating questions in cosmology. Could the properties of our universe contain clues about something beyond our universe? Scientists have looked for unusual patterns that might reveal hidden structure. The cosmic microwave background is one of the most important places they look. It is the faint afterglow of the early universe, released when the universe became transparent roughly 380,000 years after the Big Bang. Today, that ancient light fills the cosmos. It is almost perfectly uniform. Tiny variations exist. These tiny temperature differences contain information about the early universe. They tell scientists about its composition, its geometry, its expansion, and the seeds from which galaxies eventually formed. If the universe had been created through some unusual process inside a black hole, scientists might expect that process to leave detectable fingerprints. But so far, there is no universally accepted fingerprint proving that happened. This is one of the biggest problems for the theory. A beautiful idea is not enough. Science needs observations. And that is where black hole cosmology remains speculative. There is a remarkable mathematical coincidence that often appears whenever people discuss this possibility. Every mass has a characteristic gravitational length scale. For a non-rotating, isolated object, the Schwarzschild radius tells us the radius an object would have if its mass were compressed into a black hole. For the Sun, that radius is only a few kilometers. For a much larger mass, the radius becomes much larger. Now consider the enormous amount of matter and energy associated with the observable universe. If you make a simplified calculation and ask what gravitational radius corresponds to such a huge mass, you can obtain a scale that is surprisingly close to cosmological scales. That sounds dramatic. But there is an important catch. The universe is not an isolated ball of matter sitting in empty space. It is an expanding space-time described by cosmological solutions to general relativity. So you cannot simply take the Schwarzschild formula, plug in the mass of the observable universe, and conclude that the universe is a black hole. The similarity in numbers is intriguing. It is not proof. In fact, this distinction is crucial. The observable universe has a current radius of roughly 46 billion light-years, even though the universe is about 13.8 billion years old. That sounds impossible until you remember that while light was traveling toward us, space itself was expanding. So the distance to the objects whose ancient light we are receiving today can now be much greater than 13.8 billion light-years. This is one reason simple black hole calculations can become misleading when applied to the entire universe. The universe does not behave like a giant star that collapsed inside an otherwise empty space. Its geometry is different. Its expansion is different. Its large-scale behavior is governed by cosmology. So why does the black hole idea continue to attract attention? Because it touches a much deeper question. What happens when gravity becomes so extreme that the distinction between space, time, matter, and geometry begins to break down? Black holes are the closest natural laboratories we have for that question, and the early universe may be another. In fact, the two situations have something profound in common. Both push general relativity toward its limits. Inside a black hole, classical equations lead toward a singularity. At the beginning of the Big Bang, classical equations also lead toward a singularity. That does not prove the two are connected, but it suggests that the same missing piece of physics might be involved in both. Perhaps a future theory of quantum gravity will show that black hole singularities and the Big Bang are not separate mysteries at all. Perhaps they are two versions of the same phenomenon. And if that happens, the idea of universes being born from black holes could become much more than science fiction. There is another possibility. Maybe every black hole contains a universe. Think about what that would imply. The black holes we observe in our own universe would not simply be cosmic endpoints. They could be gateways to new, expanding regions of spacetime. Each one could potentially give birth to another universe, and those universes could contain black holes of their own, which could create more universes, and so on. Suddenly reality becomes something like a cosmic family tree. Our universe would have a parent. That parent universe would have had its own history. And somewhere in that history, a black hole could have formed. Inside that black hole, our universe could have emerged. This idea is sometimes connected to broader concepts of a multiverse and, in some models, even to proposals such as cosmological natural selection. The basic thought is fascinating. If universes can produce black holes, and black holes can produce new universes, then universes capable of producing more black holes might effectively have more descendants. Over immense stretches of time, universes could therefore develop statistical tendencies toward physical parameters that make black hole formation more likely. It sounds almost biological, but there is an important difference. Living organisms reproduce through known biological mechanisms. We have no evidence that universes reproduce this way. This remains highly speculative. Still, it illustrates something important about theoretical physics. Sometimes a strange question forces scientists to rethink the boundaries of an entire subject. Black holes have done exactly that. For decades, scientists thought of them mainly as gravitational objects. Then they discovered that black holes have temperatures. They can have entropy. They can radiate through quantum effects. And they are deeply connected to information. That led to one of the greatest puzzles in modern physics: the black hole information paradox. If something falls into a black hole and the black hole eventually evaporates, what happens to the information about everything that fell inside? Quantum mechanics says information cannot simply disappear. Classical black hole physics seems to suggest otherwise. Solving this paradox has forced physicists to reconsider what space and time actually mean. Some researchers now believe that space-time itself may emerge from deeper quantum information. If that's true, then our ordinary picture of the universe as a giant three-dimensional container may be completely wrong. Space could be something that emerges from more fundamental physics. And if space itself is emergent, then the question of whether the universe is inside something becomes much harder to define. Inside what? Outside where? The words themselves may stop making sense at the deepest level. This is why the black hole universe idea is so fascinating, even if it turns out to be wrong. It forces us to confront the possibility that our everyday understanding of reality is based on concepts that only work at ordinary scales. Human scales. Space looks like space. Time moves forward. Objects have locations. Causes come before effects. But near a black hole horizon, or near the earliest moments of the universe, these intuitions become unreliable. And scientists are now getting better tools to investigate these extreme environments. The James Webb Space Telescope has been looking deeper into the universe than ever before. It has revealed galaxies from surprisingly early cosmic times, and found massive black holes existing when the universe was still very young. These observations have created new questions about how quickly the first black holes formed and grew. But again, we need to be careful. JWST has not discovered evidence that our universe is inside a black hole. It has not seen the outer universe. It has not detected an event horizon surrounding the cosmos. What it has done is expose weaknesses and uncertainties in some of our models of the early universe, and that is exactly what good science should do. The goal is not to prove a favorite theory. The goal is to discover where our understanding fails. And there's another reason scientists Remain cautious about black hole cosmology. If our universe formed inside a black hole, the model needs to reproduce everything we observe. Not just the Big Bang, not just expansion, everything. The cosmic microwave background, the distribution of galaxies, the abundance of hydrogen and helium, the behavior of dark matter, the acceleration of cosmic expansion, the formation of stars, the growth of black holes, and the incredibly precise patterns we see across billions of light years. A successful theory would need to explain these observations at least as well as the standard cosmological model does. So far, no black hole cosmology model has replaced the standard picture. That is the reality. Standard model of cosmology remains extraordinarily successful. It tells us that the universe expanded from an extremely hot, dense early state. It explains a huge amount of observational evidence. And although major mysteries remain, scientists do not currently need a black hole outside our universe to explain most of what we see. So, perhaps we are not inside a black hole. Perhaps the numerical similarities are coincidences. Perhaps the Big Bang was produced by physics we haven't discovered yet. Perhaps quantum gravity will completely change the way we understand the beginning of time. Perhaps buried inside the equations, there really is a connection we have not yet recognized. And this is where the story becomes bigger than black holes, because the most important question may not be, are we inside a black hole? The deeper question is, why does the universe have the structure it has at all? Why these laws? Why these constants? Why this amount of matter? Why does anything exist? Why does the universe allow structures like stars, planets, chemistry, life, and eventually minds capable of asking these questions? We are standing at an extraordinary point in human history. For thousands of years, humans looked at the night sky and saw lights. Then we discovered those lights were suns. Then we learned that many suns belong to galaxies. Then we discovered that there are billions of galaxies. Then we learned that space itself is expanding. We detected gravitational waves. We photographed the shadow of a black hole. We measured the ancient light of the Big Bang. And now we are asking whether the universe itself might be part of something even larger. Maybe one day a new theory will tell us exactly what happens inside a black hole. Maybe it will explain the Big Bang. Maybe it will connect the two. Or maybe it will reveal something so strange that the black hole idea looks simple by comparison. For now, we don't know. And that uncertainty is not a failure. It is the frontier. Because every time science reaches the edge of what it can explain, there is a choice. We can pretend the mystery isn't there. Or we can ask a question. That sounds impossible. What if we're wrong about the universe? What if the Big Bang wasn't the beginning? What if black holes are not endings? What if every black hole is hiding a new region of reality? And what if, somewhere beyond everything we can observe, there is a universe that gave birth to ours? We may never be able to see it. If an event horizon truly separates our universe from whatever came before, information from the outside may be permanently inaccessible. But even if we can never look beyond that boundary, the universe may still contain clues. In the arrangement of galaxies, in the oldest light we can detect, in the behavior of black holes, in the laws of physics themselves. Perhaps one day those clues will fit together. Maybe they will tell us that we really are living inside an enormous cosmic black hole. Maybe they will completely destroy that idea. Either answer would be extraordinary, because the greatest discoveries in science do not simply give us new facts. They change the questions we are capable of asking. So the next time you look into the night sky, remember something. You are not looking at a simple collection of stars scattered through empty darkness. You are looking across billions of years of cosmic history. You're looking at a universe that began in an extreme state we still do not completely understand. And somewhere in that universe are black holes, objects so extreme that our best theories begin to break down. Maybe they are cosmic graveyards. Maybe they are gateways. Maybe they are the seeds of new universes. And maybe, just maybe, the universe you call home was born inside one. We don't know, but that's what makes the question so powerful. Because if the answer is yes, then the biggest object you have ever imagined, the entire universe, might itself be part of something even bigger. When if the answer is no, we are left with an even more unsettling possibility. that whatever created our universe may be something stranger than a black hole, something our current physics has not even learned how to describe. And that means the greatest mystery may not be hiding somewhere billions of light years away, may be hiding in the very nature of reality itself.